Welcome to this video on linear motion. In this video, we will explore key concepts including distance, speed, velocity, and acceleration. This video covers the fundamentals of movement and position. We will learn how to interpret distance time and velocity time graphs, understand the relationship between distance, speed, and time, and use the formula for acceleration. Average speed is calculated by dividing the total distance moved by the time taken. In physics, speed is typically measured in meters per second. You can rearrange the speed formula to find distance or time. Using this triangle, distance is speed multiplied by time, and time is distance divided by speed. When converting units, remember that 1 kilometer per hour is approximately 0.28 meters per second. Conversely, 1 meter per second is 3.6 kilometers per hour. Let's calculate the average speed of a car that covers 500 meters in 20 seconds. Dividing 500 by 20 gives us an average speed of 25 meters per second. Here is our second example. If sound waves travel at 340 meters per second, how far will they travel in 1 minute? To solve this, we multiply the speed of 340 meters per second by 60 seconds, which equals 1 minute. The result is 20,400 meters, or 20.4 kilometers. Try completing this table to practice calculating distance, time, and average speed using the formulas we have covered. Here are the completed values for the table, showing the relationships between distance, time, and speed across various scenarios. This graph illustrates distance over time. As you can see, the relationship between these two variables is clearly represented visually. On a distance-time graph, the slope or gradient represents the speed. A steeper slope indicates a higher speed, while a shallower slope indicates slower movement. The gradient is equal to the speed. For example, in this graph, a change of 150 meters over 10 seconds results in a speed of 15 meters per second. Let's sketch distance-time graphs for 3 different scenarios: a car at a steady speed, a bus moving faster at a steady speed, and a lorry accelerating from rest. As shown on the axis, the car and bus have straight-line graphs representing constant speeds, while the lorry shows a curve indicating its increase in speed from rest. Now let's analyze the motion of 3 different lorries, labeled X, Y, and Z, based on this distance-time graph. By examining the slopes, we see that lorry X is the quickest, moving at 25 meters per second. Lorry Y moves at 20 meters per second, and lorry Z is the slowest, with intervals of speed, a stationary period, and an overall average speed of 11.1 meters per second. Let's review these concepts by filling in the blanks. Speed is distance divided by time, and on a distance-time graph, the slope represents the speed. Here are the completed terms. Speed is distance over time, measured in meters per second. A gradient of 20 meters per second equals 72 kilometers per hour, or approximately 40 miles per hour. Moving on to velocity, it is defined as speed in a given direction. Even if an airplane loops at a constant speed, its velocity changes because its direction of motion is constantly shifting. Consider a stone dropped from a cliff, falling 20 meters in 2 seconds. Its average downward velocity is 10 meters per second, while its horizontal velocity is 0 meters per second. Next is acceleration. Acceleration is the rate of change of velocity, calculated as the change in velocity divided by the time taken. Its units are meters per second squared. Why is acceleration measured in meters per second squared? Since velocity change is in meters per second and we divide by time in seconds, we arrive at meters per second squared. Remember that deceleration occurs when speed decreases over time. Also, circular motion at a constant speed involves acceleration because the direction is continually changing. Let's apply these formulas. We can complete this table for an airplane accelerating at 8 meters per second squared. Here is a practice problem. Calculate the acceleration of a car that changes its velocity from 5 meters per second to 25 meters per second in 4 seconds. Using our formula, we subtract the initial velocity of 5 from the final velocity of 25, then divide by 4 seconds. This gives us an acceleration of 5 meters per second squared. For our next challenge, calculate the final velocity of a train accelerating at 0.3 meters per second squared for 60 seconds, starting from 5 meters per second. Multiplying the acceleration by time gives us a change of 18 meters per second. Adding the initial 5 meters per second gives us a final velocity of 23 meters per second. Finally, calculate the deceleration of a car slowing from 18 meters per second to a complete stop in 3 seconds. To find the deceleration, we calculate the acceleration. 0 minus 18 divided by 3 seconds gives negative 6 meters per second squared. Therefore, the deceleration is 6 meters per second squared. Let's review these concepts by filling in the gaps. Velocity is speed in a particular direction. A person walking north has zero velocity in a westward direction. Acceleration is velocity change divided by time, measured in meters per second squared. Deceleration occurs when slowing down. A body can accelerate even at constant speed if its direction changes, like in a circle. Moving to velocity time graphs, the slope of the line represents acceleration. Steeper slopes mean higher acceleration, while a horizontal line shows constant velocity or zero acceleration. Crucially, the area under a velocity time graph represents the total distance traveled by the object. Let's sketch a graph for a car accelerating from rest to 15 meters per second in 3 seconds, then maintaining that speed for 1 additional second. Now use this graph to calculate the acceleration and the total distance traveled after 4 seconds. The gradient gives an acceleration of 3 meters per second squared. The area under the triangle, calculated as half base times height, shows a distance traveled of 24 meters. Next, calculate the acceleration and distance traveled using the data provided in this graph. The slope gives an acceleration of 1.2 meters per second squared. The total area is the sum of the rectangular and triangular sections, resulting in a distance of 80 meters. Finally, determine the distance traveled over 15 seconds and the deceleration during the last 5 seconds from this graph. The area shows 250 meters traveled. For the final phase, the slope of negative 4 meters per second squared indicates a deceleration of 4 meters per second squared. Distance time graphs are also useful. The gradient of these graphs is directly equal to the speed of the object. Similarly, the gradient of a displacement time graph equals the velocity. For an object thrown upwards, the gradient decreases until it reaches 0 at the peak, then becomes negative. To wrap up, examine this displacement time graph to describe the motion, acceleration, constant velocity, deceleration, rest, and finally, acceleration back toward the start.